Hi guys, today we are going to talk about Hooke's law, a little bit of Hooke's law, but mostly elastic energy. So this is really the energy that's stored in the stretching or compressing of a spring. We're going to go into the calculations, the equations, how do we solve for it, how does it relate to forces, so let's get going. So Hooke's law, friendly reminder, we're just going to do a little bit of review because I didn't test you guys over springs last semester. I didn't really throw it on anything because we're going to hit it super hard this semester. So reminder, if an object causes a spring to stretch or compress, the spring exerts an elastic force on the object. So we could imagine, let's say we've got an object and we've got a spring and there's a block here. Let's say the spring, if we're going to draw a force diagram, we'd have force gravity up, force spring up, whoops, and we'd have force gravity downwards. So if it's at rest, we know these forces are going to be equal to each other. So we're going to actually derive Hooke's law from a graph. We did this in a lab. We had a lab where we had force in newtons here and the spring force because we stretched the spring and measured how far. And then we've got our change in position, which would be meters. We're going to have our data is going to fill up here. And we had our slope represent something. Now, if we think about if this is a linear graph, we've got y equals mx plus b. We don't have a b value here because we're going to say that it's going to be equal to 0. We have spring force on our y-axis. On our x-axis, we actually have a change in position in x. And our slope, if you remember, was k, which was the spring constant. So that's a quick reminder of where Hooke's law came from. Hooke's law is the spring force is equal to K times delta X. Now you might see on the equation sheet that there's the absolute value signs around this because if we were to compress it, that's supposed to be an absolute value sign. If we were to compress it, it would just be like compressed or stretched. You decide the direction based on which way does it naturally want to restore. So if we're just looking at the magnitude, we put the absolute values bars around it. If we want to figure out the direction, just draw your force diagram. Like in this situation, I would see that my spring force was up. That's where Hooke's law comes from, right here. This is Hooke's law. Quick reminder that it's there. All right, so that is Hooke's law. Sorry if there was a little pause and a break there. I had someone come in, so I had to pause my recording. So let's use this idea of Hooke's law, and we're really going to jump into deriving elastic potential energy. So I'm literally going to keep this information up because we're going to use this. Now, we learned in our work lesson that work is equal to the area under a force versus displacement graph. So work would be this area here. So we know that the change in energy is equal to work. Now looking at this, I know that my work is going to be 1/2 my base times my height. So we're trying to come up with this equation. Now, 1/2, my base is delta x. And my height is force. But I'm going to use this spring force equation here because I know that that's what my force would be. I'm going to say K delta x, which when I rearrange this, you see there's 2 delta x's. We're going to get 1/2 K. And I'm going to get rid of the delta x. I'm just going to say x squared. This is my spring force equation right here. That's where it comes from. It's not me pulling an equation out of thin air. It's literally me using the idea that work is equal to the area under the curve. And if we have a spring, that curve's going to look like a straight line, and then plugging in that spring equation, that spring force equation into there. So let's actually do some problems with this. So I've got 2 examples. The first one, a spring below has a constant of 10 newtons per meter. If the block is pulled 0.3 meters horizontally to the right and held motionless, what force does the spring exert on the block? So we're first going to sketch a diagram so we can wrap our head around the problem. I've got my block, so we've got force gravity, we've got normal force. There's some sort of applied force this way. Let's call it a P, force push pull. And then in the opposite direction, there's going to be a spring force because that spring's going to want to go back to its natural position. we know that the forced spring is going to be equal to the applied force. So if we want to solve for what does the spring force exert, we can just say spring force is equal to K delta X, and K is 10, delta X is 0.3, which gives me 3 newtons. Now, if you want to know where the newtons comes from, we've got newtons per meter. Oop, that's not a meter. Newtons per meter times meter. The meters cancel out, which is where I get my newtons from. That should be review. Now we want to go how much energy is stored in the spring when it's stretched to 0.3 meters. So we just on the last slide determined that the spring energy is going to be 1/2 kx squared. So I'm going to say 1/2. My k is 10 and my x is 0.3 squared, which gives me a spring energy of, I gotta plug in some numbers because I didn't do this one beforehand, 0.5 times 10 times 0.3 squared. So we have 0.45, and our unit for energy is joules. 0.45 there. We could also say Newton meters, but typically when we're talking about energy, we're going to use the term joules. When we talk about work, we're going to use Newton meters. So that's our first one. Let's try another example. So the spring below has a spring constant of 20 newtons per meter now. The friction force between the block and the surface is 4 newtons, so that's my force friction. What is the maximum distances the spring can be stretched from equilibrium for the box to begin to slide back? So we've got force gravity, we've got force normal, we've got an applied force because we want to know what that force would be. Yeah, we want it to be stretched, and then we want it to be able to hold and then let go of it. So basically, we are going to look for, and this would be a force friction, and this would be a force spring. We're basically want to know if I pull it back and let go, where is it going to hold until I get to? And we want these two forces basically to be equal to each other. Because I want to say the sum of my forces in the x direction are going to be equal to 0 because we want them balanced. So the friction force minus the spring force, they should be equal to one another. But if friction force is equal to spring force, and we want to find the max displacement, if the friction force is 4, that's the max friction force, that's the friction force between it. I want to know how far to stretch it. We can just say K delta X here. So we can say 4 is equal to 20 times delta X, divide the 20 to the other side. So my max displacement I can have, it's going to be 4 divided by 20, which is 0.2 meters. That's the max that can be displaced. Reviewing those forces while we're doing this. Then what energy stored at the spring at that distance? We're just going to use our 1/2 kx squared. This, with the spring energy, it's going to get more complicated, but I just wanted to kind of introduce you guys to the idea of spring energy before we jump into the deep end of combining all the energies. So the next lessons, we're going to focus in on each energy, kind of like we did with forces, and then we're going to dive into the last lesson of combining it all together. So I'm plugging this all into my calculator to give me an energy of 0.4 joules. All right. That's really all I have for spring energy for you guys. It's really keeping the idea, it's 1/2 kx squared, and then knowing that you can combine Hooke's law and spring energy together.